Okay, I think we can get started.
Great. Okay, everyone. So this webinar will be recorded. And we will be sharing the recording across some of our platforms. So in any case, welcome everyone. My name is Helen Yang. I'm an assistant at the Northeast Big Data Innovation Hub and a student at Columbia University. And this is the April 2021 COVID Information Commons Research Webinar. This is part of a webinar series brought to you by the 4 Big Data Innovation Hubs, which includes the Northeast Big Data Innovation Hub, the Midwest Big Data Innovation Hub, the South Big Data Innovation Hub, and the West Big Data Innovation Hub. And this webinar series and also the COVID Information Commons is sponsored by the National Science Foundation Convergence Accelerator. So every month we bring together a group of researchers studying various topics related to COVID-19 to share their findings and also some of their collaboration opportunities. So we welcome you again. And to get us started, I'd like to introduce the Executive Director of the Northeast Big Data Innovation Hub, Florence Hudson, to give us a little bit more information about the COVID Information Commons. So Florence, if you want to take it away.
Excellent, Helen. Thank you so much. And we can go to the next slide. Wonderful. So thank you, everybody, for joining us. The COVID Information Commons was funded by the National Science Foundation in May of 2020, and we launched it in July of 2020 as well. And it provides an open resource to explore NSF-funded research addressing the COVID-19 pandemic. I'm happy to say that we are now looking at how we're going to include NIH, or National Institutes of Health Awards, in here as well. And we've started proactively inviting our NIH colleagues who are doing COVID-related research to join these webinars and to present on future webinars. So if you're an NSF-funded COVID-related researcher or NIH, please let us know if you'd like to present on a future webinar, because we leverage these webinars to help you all come together as researchers and practitioners to leverage all the great research going on in COVID as we continue to try to address this terrible pandemic. And we expect this to continue at least throughout this year. So if you go to the COVID Information Commons, you'll be able to find an NSF Awards and PI database. We actually have PI surveys filled in by about 250 of the principal investigators. And you can learn about their research results, collaboration opportunities, and we're hoping to get more PIs answer the survey as well. You can also look at machine learning generated maps regarding the different COVID awards in the NSF database at this point to look for congregation around some of the clusters of scientific domains that you might be working in, as well as there's a simple search mechanism that's specifically COVID awards into the different directorates of NSF. We're looking at how we can expand this for NIH as well, as I mentioned, perhaps other vetted awards in the future. So we're delighted to have this opportunity to bring you all together to help you meet each other, collaborate with each other, and address the COVID pandemic. And I really want to thank Helen Yang, who, as she mentioned, is a student on our team from Columbia University, for managing this entire event for us. Thank you so much, Helen, and for all of our speakers today.
Thank you, Florence. And again, thank you to all of our speakers who are joining us today. Brian Cheng from Clark University, Lalita Shankar from Arizona State University, Song Gao from University of Wisconsin-Madison, Dan O'Brien from Northeastern University, Colby Ahn from AC Adacol Inc., Jaideep Vaidya from Rutgers University, Newark, and Olga Wilhelmi from the University Corporation for Atmospheric Research. So the researchers will be happy to answer your questions in the chat after each of their presentations, and we'll be going over any unanswered questions at the end of the webinar. So without further ado, let's get started with Brian Cheng from Clark University. Brian, welcome.
All right, hi everyone. My name is Brian Cheng, and I'm a postdoc working with Arshad Kudrali, who is the PI of this NSF grant, which is called Predicting Coronavirus Disease Impact with Multi-Scale Contact and Transmission Mitigation. And this talk is just going to be an overview of all the work that we have been doing in the past year, actually. And it's really broken down into 2 different teams. So we have this physics team of excellent undergraduate and graduate physics majors here at Clark University. And we have a medicine team made up of doctors and nurses and respiratory health practitioners as well from the University of Massachusetts Medical School Bay State. And in this image below, you can see that there's a our artificial sneeze with a long exposure, which we'll talk about more later on. So the main point of this grant initially is to develop a stochastic model to predict how the coronavirus spreads from two different populations. So if you imagine here, this is Boston, for example, and over here, this is Worcester, Massachusetts. Then we're trying to figure out how the coronavirus or how any disease spreads from one population to another. And as we were developing these models, we started to realize we can plug in pretty much any parameter we wanted to predict how, or to match how the coronavirus has spread based on past outcomes. But that really got us thinking, what are some of the mechanisms for these parameters? And really, how can we use fluid dynamics and soft matter physics to help predict future outcomes? And so we went about this by developing some experiments, some physical modeling to determine the spatial temporal dispersal of mucosalivary droplets. So over here, we have an artificial sneeze, the evolution of our artificial sneeze cloud over time, and which was matched with human sneezes. So it was matched with human sneezes in literature. And really what we're interested in doing is trying to determine how these sneeze droplets would spread depending on exhalation strength, mucus rheology, and also the different mitigation strategies we can employ to reduce the dispersal of mucosalivary droplets. And really this is important because we need to develop a systematic measurements of the droplet dispersal travel distances and how long the droplets stay in the air, and also the evaporation rates as a size of the droplet, as a function of this droplet size distribution, in order to really fully characterize the transmission rates in our stochastic model. And this is really important because we know that inhalation of these virus-laden droplets is the main mode of transmission for COVID-19 spreading. And it's also very important for various other diseases that are transmitted by inhalation of other people's exhalations, such as tuberculosis and influenza. So this has importance for future pandemics and future health crises as well. So one of the first things we did was really look at the spatial dispersal. For example, how far do the droplets go and where do they end up landing? So one of the key questions we're interested in is how does the rheology of the fluid affect the dispersal patterns? So here we have simply just water being exhaled outwards. And then as we increase the mucin concentration, basically the stickiness and the of the fluid, we start to see different dispersal patterns. And one of the key features is that as you increase the mucin level to someone who is relatively unhealthy, then we start to see narrower lobes or narrower dispersal patterns, but the droplets travel a much further distance. So what we start to, and another thing you might notice is that the number of large droplets, these speckles that kind of look like stars, the number of these large droplets start to increase as well once you start reaching higher mucin concentrations. And we've also started looking at the temporal dispersal. In other words, how long do they stay in the air? So if we look at the falling speed of a sneeze cloud versus the size of the cloud, we can see these trends that occur, and we can model these quite accurately as well. And you can find more information in this paper that we published back in October 2020. Furthermore, we've been collaborating with doctors at UMass Medical Hospital to determine how aerosols are escaping from these oxygenation devices. For example, here you have a nasal cannula, which is these tubes that go into your nose. And we put this onto a medical mannequin, and we show that the aerosols can travel quite a distance. So you can imagine if there was a healthcare worker standing right above this patient, then they would get direct direct exposure to the aerosols. But just by placing this mask over the patient, we can reduce and redirect the aerosols. Furthermore, we have a simple oxygen mask, which sprays the aerosols in 2 directions. And then once again, we placed a mask over the simple O2 mask to redirect the aerosols. So overall, we were trying to use fluid dynamics and soft magnetic physics to plug in as parameters to improve these transmission rate models for disease transmissions. And thank you for your time, and I'll be happy to answer any questions.
Thank you so much, Brian. So next up, we have Lalita Shankar from Arizona State University.
Hi, everybody, and thank you, Helen and Florence, for giving me this opportunity today. So this is an NSF grant, a rapid grant funded through SATSI with my awesome colleagues, Ni Tru, Ming Zhao, and Visar Berisha. Ni and Ming are in computer science, and Visar is in the College of Health Solutions. As the name suggests, we're going to be doing a lot of deep dive into machine learning and use that to do a more holistic contact tracing. So there's actually 3 aspects to our work. We're trying to enhance existing contact tracing protocols by using both Bluetooth and GPS, and I'll dive into it in a moment. The big idea here is to say, can you ride or piggyback on surveys that are being done on campuses across the United States, particularly at ASU? We have a daily health survey we have to take. Can you use that kind of survey data, use it to both build a baseline risk model and then combine it with mobility and even phonation, which is a biomarker? Just like the nasal thing, it turns out phonation is a biomarker for a whole bunch of respiratory and even mental health issues. And combine that to build hotspot models and so on and so forth, and continue to evaluate risk and put up a risk score. And our overarching goal in this work is actually to take this build system and deploy it into ASU's mobile app, and that's an ongoing process. So very briefly on contact tracing, existing contact tracing apps basically use Bluetooth. There are these tokens that are used. I don't have time to go into it, but they are vulnerable to security attacks. They also, because they do not use GPS, they cannot evaluate infected hotspot locations except through, say, cell towers and stuff like that. So they're not really exploiting a lot of rich user-specific data. And our goal in this project was to actually combine Bluetooth with GPS, which exists, but we've been able to build this protocol, test it on Android devices, and provide strong privacy guarantees. And the other side effect is we can also now compute a histogram of infected hotspots using secure aggregation techniques at multiple of these servers, the back end servers. Okay, so that's on the contact tracing part. On the device part, our goal is actually to come up with a risk prediction model. And what are we going to do? We want to have a baseline risk that's based on your health symptoms one time, but daily symptoms will be used to continually assess this risk. Can use mobility patterns, especially on a university campus, to figure out if there's an outbreak at any dorm or any place, how can we, even move traffic around? And ultimately, our goal is really to do phonation-based risk indices. And I will not have the time to talk about this in great detail, but the whole point is to breathe into, use our app to just say an ah for, a few seconds, and use that to look at both respiratory health issues are directly correlated with how you phonate, and it's also correlated rapidly with brain fog now. So there's a lot of research here, and Vishar, my colleague, and I are working on this. Okay, so I'm going to do a deep dive into only one thing in the interest of time, which is how do you use surveys to predict risk. And we've been very lucky because thanks to this grant and a grant from Google's AI for Social Good, we were able to participate in a competition that Facebook hosted and get a data set from Facebook that CMU Delphi has been collecting for them through the Facebook app. And basically this is a survey, it's a daily survey, and they've had 18 million responses with 53,000 participants. And the whole idea is to collect a whole bunch of symptoms-based survey, prior health conditions, social distancing, mental health, demographics. And of all that, there's only about 900,000 that are people who've taken the test. So that's the data we use, because that's the label we use to predict whether somebody, well, based on your symptoms, whether you may be at risk for COVID. So what are we doing? I'm diving a little bit deeper into what kind of models we're using. We're going to use XGBoost because this is a kind of healthcare data set. It's got a mix of, a discrete and continuous value data. But XGBoost is a fantastic, very well-known, robust algorithm. What we're going to do is, in fact, make it even more robust by using a whole class of loss functions that we've developed, and I'm happy to take that offline. And in short, what we've been able to show is that even restricting ourselves to the top 8 symptoms, and this is a very imbalanced data set. We have 86% negative, only 14% positive labels of the people who've taken the test. We can enhance existing XGBoost with even better things using our loss function. Even more interesting, what we've been able to do is in reality, the survey data is very noisy. We did a lot of pre-processing, but can you actually continually do this while the data is noisy? So we tested our algorithm against noisy labels, where we flipped a bunch of labels. We kept it. We did 2 experiments, stratified and unstratified. We kept the imbalance, and we have some very good results. So in the interest of time, again, I'm going to stop it there and take it offline. Our holy, the grail of this project, if I may, is to combine all these 3 things, put it on the ASU app, and be able to give the user a survey risk, and basically do a lot of back-end data collection for ASU. So we're a little bit away from that, but we have our IRB approved, so we're hoping to put an app in and do stuff. So I'm going to stop right there. Thank you very much.
Thank you so much, Lalitha. And again, as a reminder, please feel free to add any of your questions in the chat. Great. So next up, we have Song Gao from the University of Wisconsin-Madison.
Thank you, Helen. Hello, everyone. My name is Song Gao. My topic today is mapping human mobility and close contacts for the geospatial modeling COVID-19 spread. This is a joint work with my colleagues, with Qing Li from mathematics, Kaibing Chen from life science communication, and Johnson Pats from public health. So all of us are at the UW-Madison and funded by NSF as a social and behavioral science. So this is a different aspect that are very relevant to previous talks. And for us, at the beginning, during the pandemic, first thing we are interested to look at how different community neighborhoods responded to the stay-at-home or safer-at-home orders. So by tracking the mobility patterns, as you can see from the dashboard, and if the color shows blue, mean that on particular day on particular county, there is a reduced mobility measured by the median or the individual maximum distance, and the red color shows the increased mobility. By tracking the mobility patterns, we can further associate the mobility pattern with COVID-19 confirmed case growth rate. And what we found was that there exists a statistically significant association regarding the mobility pattern and then the COVID-19 infection rate, although with some temporal lag. And if we compare the before stay-at-home and after stay-at-home order, we found that the doubling time, increase, which also shows the effectiveness of the stay-at-home orders. And then, in order to do the modeling, one critical data set was missing from the open mobility data set is about the travel flows between different places. So this is why we collaborated with SafeGraph and to aggregate the anonymized mobile phone data and to provide the state-to-state and county-to-county and also the track-to-track spatial interaction flow data set. And this is an open data repository available on GitHub. And we still maintain the weekly updates, but the resolution is daily updates. And if people are interested, you can still incorporate this data set into your research. And at the local level, in addition to the travel distance and then the stay-at-home time, we also utilize individual level mobile phone data to measure the close contacts information as a proxy, whether they are crowd events. As you can see on the map, this is around our University of Wisconsin-Madison campus area, also the downtown of Madison. And as we know, there was a surge in last summer when our campus reopens. So this is why we hope to utilize such a mobile phone tracking platform to understand whether people have some gathering events. And as you can see from the map, we measure at the specific sensor tracked block groups, and the darker the color is, and then the higher of the close contact is, mean that there might exist some gathering. So this is as a proxy and to inform some of the local decision making. And utilizing the mobility and then the close contact information, we further build a mobility augmented traditional SAER or epidemic model to understand the geospatial spread of the disease. And one innovation of our model was that we specifically take the spatial interaction we mentioned earlier into the this compartment modeling effort, and to consider the impact of the interstate travels. And so we evaluate 3 specific measures: travel flow restriction, the testing or reporting rate, and the social distancing policy, which is directly linking to the transmission rate. And so what we found was that actually the travel flow restriction, regarding the impact, is not as important as the social distancing and also the testing and reporting rate. At the beginning of the March 2020, in the US average, there are only about 22% of the confirmed cases has been reported based on our modeling effort. So as shown in the plot on the right, we also quantify the impact of the timely quarantine and isolation of the infected cases. And the x-axis shows the delay in time of days, and the y shows the logarithm of the set stat of people. So you can see that on some states at that time, like New York and Michigan, if the infected cases not isolated or quarantined in about 2 days, then the majority of people in these 2 states will be largely infected. So again, to show the importance of the timely quarantine and isolation. So finally, at the inter-county level, we also take the spatial heterogeneity into consideration in our modeling effort. Specifically, these are 2 typical counties in the Wisconsin. So the Dane County, as we know, there is a large age structure heterogeneity because of the existence of their university, and versus Milwaukee County, we know that Milwaukee is one of the most segregated metropolitan area in the U.S. So there is a large race and ethnicity heterogeneity. So this is why if we compare the COVID-19 infection rate versus the spatial heterogeneity of the race and age structure, we can find they actually correlate with the infection case very well. So again, we try to use different demographics to explain the spatial heterogeneity of the COVID-19 spread. So that's all for my presentation. Thank you for your attention.
Thank you very much, Sung, for sharing your research. Okay, so next up we have Dan O'Brien from Northeastern University.
All right, I'm unmuted, I think. Can everyone hear me? Okay, great. Getting started. So Inequitable consequences of uneven vaccination intentions. So I'm presenting this work on behalf of myself, but also my colleagues Ki Wong and Alina Risti from Northeastern University, also affiliated with the Boston Area Research Initiative, which is a center that I direct there, and Russell Shute and Lee Hargraves from UMass Boston Center for Survey Research. So jumping in here, right, this doesn't need too much preamble, being that all the talks are about COVID, but this is the Boston Globe headline from March 11th last year. Shut down, right? Everything shuts down, right? The world shuts down. And like everyone else on this panel, the question that struck me after a few days was, how does an academic center help, right? What do we do to contribute in this moment? And especially because I myself, unlike some of the others, I'm not a public health researcher. I'm not an expert in disease transmission. And so then what do we do? Right, so what we decided very quickly was we needed to be a data support system in a pandemic. We needed to bring together as much information as possible to understand the social and individual dynamics that were shaping and being shaped by the pandemic. And so this included a neighborhood survey on COVID experiences, social distancing, and risk exposure in order to understand how these varied by neighborhood. This was funded by an NSF rapid grant. Case record sharing with the Boston Public Health Commission related to the survey, but giving us access to the case records themselves. We accessed mobility flows from cell phones, much like Dr. Gao's work, using things like SafeGraph and cubic data to approximate networks of exposure and activity patterns. And we built on an existing NSF grant to build what's called the Boston Data Portal, which we extended to a COVID in Boston database for research and teaching. And we gathered basically every administrative and internet gathered data set we possibly could over the course of a 4-month period, including 311 calls, 911 calls, building permits, tax assessments, Craigslist postings, Airbnb postings, Yelp reviews, and some others. And that's actually publicly available. That's been published, and people can access that at will, and please do. So what did we do with that then, right? We wanted to have impact. And so we've written some academic papers as well that are in the pipeline or under review, but we really went whole hog on public reports to try to have impact locally. So we published 8 of these for inequities in navigating a pandemic, one on fear and ambivalence towards the virus, another one on economic impact, another one on how lifestyle, ideology, and context are influencing people's social distancing behaviors and attitudes, another on vaccination planning and hesitancy, one on physical and mental health impacts across communities, one that I'm going to speak about today, the inequitable consequences of vaccination intentions, and last one, a little bit different from the others, the responsibility of the large landlord addressing the impending eviction tsunami people have been talking about once the CDC moratorium goes there. So we want to have public impact, and so all of these are out there. They're all published. They're all up on our website, at the center's website, and also in preprints. But today, I just want to kind of wrap up by showing one example of something we did that really brought together all of these data sets on the inequitable consequences of vaccination intentions. Right? And so the whole premise here was, right, vaccination is the light at the end of the tunnel, right? It's what we're going through right now, and we hope it ends the pandemic or slows it down enough that we can return to some form of normal. But lots of Americans are hesitant about getting vaccinated. And this, especially in January, and now as well too, especially concentrating communities of color, right? Those communities that were most impacted by the pandemic also are the ones most hesitant about getting vaccinated. And then the question was, can we quantify the consequences? And I put this picture in here because it's just so illustrative. About 6 to 8 weeks ago, Boston opened a new vaccination center in the heart of Roxbury, which is kind of the cultural and historical hub of the Black community in Boston. And this was the line on opening day. Very few people showed up, and as you notice, half of them were white and came from other neighborhoods because they heard there were appointments. So how do we quantify this? So we ran a simulation model, a pretty traditional susceptible infection recovered model, probably very similar to what Dr. Gao was working with. But we added in mobility-based transmission, and then we incorporated a vaccination rollout that we assumed would take 3 months, and we defined communities as zip codes in Boston plus 104 municipalities in the region. And then in order to, when we did 3 months rollout, I already said that. And then in order to make this happen, we used multiple data sources. We used historical infection cases to estimate transmission and recovery rates. We used historical mobility data to estimate cross-community transmission. And then we took our survey and we looked at people's responses about vaccination intentions, and we split those by race. And we had responses that were yes, no, and maybe. And what we did in the model was we allowed people who said maybe to be persuaded to yes, based on how many people in their neighborhood had been vaccinated at that time. So then what do we learn, right? So the first discovery was bottlenecks in vaccination. We've been seeing that on and off the last few months, right? All communities hit a bottleneck, everyone. Further vaccination at that point depends on persuasion. You can see this in the graph where there's this kink right here around 50 days or so for most communities. But if you notice, right, this dotted line here is for communities of color, and they hit the kink more around 40 days, right? About 15 days before predominantly white communities. So it arrives earlier, and this has a double whammy effect where not only do you hit it earlier and therefore make less progress, you have less persuasion because you have fewer people vaccinated at that point, according to the assumptions of the model. And so you fall further behind in those communities. Second was consequences for infections, right? Infections remain higher and persist longer in communities of color. So the gold lines here are under a circumstance with no vaccination. As you can see, it's just sort of off to the races. And again, the dotted line is communities of color, quite a bit higher. But the blue-green line is with vaccination. You see, eventually vaccination really does have impact, but that dotted line is still above the other lines, and considerably so for quite a while, and takes longer to reach the asymptote at the bottom. And if we look at the cumulative impact of this, right, we get basically a layer cake, right? Your green lines here are communities of color, and they are seeing way more total infection over the course of the simulation than your purple lines, which are communities that are predominantly white. And last, herd immunity, right? So we estimate herd immunity as reaching a point where there is fewer than one infection in a community. And what we see is stark disparities in the attainment of herd immunity. Right? The average difference of 45 days between predominantly white communities at the top and high Black Latinx communities at the bottom. And depending on how you play with the assumptions in the model, which I can talk more about offline, it only gets worse, right? And even the best case scenario only narrows this by about 10%. And so you're seeing a real challenge in getting to an equitable outcome. So in conclusion, vaccination will lead to herd immunity for everyone, but there will be inequities in getting there, and we're seeing that play out right now. Bottlenecking vaccination is critical for all communities, and this is a logistical challenge, but it's also a messaging challenge. How do we get out ahead of the bottleneck? And the last one is a need for well-crafted, compassionate messaging. And it turns out that the biggest hurdle was not the maybes, it's the no's. It's the percentage of people who are saying absolutely not, because they can't be persuaded according to the model. And I love this picture, and I end on it because this is a prominent Black minister in Boston. And in January, he sat down and he got his vaccination publicly videotaped so he could show to his community that this was safe and that this was something that needed to happen. And I think the attitude we have to take towards this is not, blaming the communities that are having difficulty determining whether this is something they feel safe with, but really reaching out to them and the challenges they're facing in order to bring everyone to the herd immunity in the end, as it were. So thank you, and happy to answer any questions offline. And just again, and all my partners.
Thank you so much, Dan. I believe we already have quite a few questions for you in the chat. Great. So next up, we have Colby on from AC Article.
Hi, yeah, my name is Colby An. I'm CEO of AKRACO, and CoPI is my our CSO Roscoe Lindstad, and we start a company when I was a faculty at UC Santa Barbara in 2016, based on bio-inspired surface treatment technology. And when there are pandemic, we thought we could help to address the pandemic using our technology, which is surface coating. And as we already experienced, CDC doesn't really help, is because they said initially no mask, even though we know covering.
Oops, Colby, I think you're cut off. So
I think I heard him coming back, but he's not moving yet. Maybe we should go to the next one, and then when he rejoins us, he can present again. Helen, what do you think?
sure, yeah, if that'd be all right. Okay. All right, then so we'll return to Colby. Great. So then next up, Jaideep Vaidya from Rutgers University, New York. Jaideep, are you ready? Thanks to everyone for bearing with us through everything that comes with the live webinar.
And the technology always wins, right?
All right, are you guys able to see the presentation?
Yes.
Okay, perfect. All right. Hello, everyone. I'm Jaideep Vaidya. I'm the director of the Rutgers Institute of Data Science, Learning and Applications. And this is essentially our response to the pandemic, what the Institute tried to do to help with respect to this. And this is joint work with my colleagues in the School of Public Health and the School of Communication and Information at Rutgers. So I did want to talk about one of the key problems that we saw essentially all through last year as the pandemic sort of unfolded, and that was the issue with insufficient testing and preparedness. And effectively, this was visible this was reported on by all of the news media, whether it was conservative or liberal. In fact, the New York Times put this up, is your state doing enough coronavirus testing? And the answer, of course, was no at the start of the pandemic, but for quite a long period of time, all the way through the summer as well. And even the Wall Street Journal sort of reported that, hey, we really need to carry out sufficient amount of sort of COVID testing in order to bring the economy back on track. So, from a technology perspective, technology tried to sort of come to the rescue with respect to this, given the lack of resources. And what happened was we saw quite a few apps like COVID Near You or How We Feel that came up, which were basically symptom tracking apps. You would report your symptoms, and then that information would be aggregated and reported back. Even the CMU app, which Facebook put out, had this interactive map and dashboard. So you would put in your information, it would then be aggregated and then released, essentially. So one huge problem that we saw with respect to this was privacy. So essentially, giving in this information, there was a lot of concern, and correctly so, regarding what would happen to your privacy as you reported such information. And in fact, there was a second problem as well, that the apps were basically predefining regions. You would get reports for your city, for your state, for the county, but at fixed sort of levels. So what we wanted to look at two different things. One was to answer this question of specific areas. If you are interested in your local neighborhood, or you are interested in a particular region of interest, what was happening with respect to the symptoms. So suppose you had this question, how many people reported feeling symptoms in the past 8 days in New York City? Or you wanted to look at your local neighborhood or across the state, what have you. So we wanted an arbitrary number of queries differing in both sizes and regions. I could ask for this, I could ask for this, maybe the whole map over there, something small over there, what have you. But you quickly realize that once you allow these sorts of queries, any number of such queries, the privacy problem actually gets way more magnified as well. So essentially, no sort of simple aggregate and release mechanism is ever going to be able to fully protect your privacy. In fact, with a very small number of queries, I can quickly figure out if particular information regarding you, or whether or not you are contributing your data to a survey like this. So what we came up with was actually an app and a framework called COVID Nearby. And basically what we are providing is a formal guarantee called differential privacy. This is a state-of-the-art model that the US Census is using. In fact, companies are using as well. And it essentially guarantees, I won't go into the math, but intuitively speaking, it guarantees that whether or not you put in your information into any such app or any such collection of data, any such survey, your risk or the risk to your identity is not magnified. You don't have a larger risk simply because you're part of the survey. It's going to be essentially very similar to even if you're not sort of participated as part of this. So what we wanted to use was differential privacy, and this is a formal guarantee. It's very nice because it guarantees your privacy against privacy attacks today, but also privacy attacks that may be invented way ahead in the future, which we know nothing about. One problem, however, is that once you try to do this, especially over such spatiotemporal data and over dynamic data, it is very, very difficult to provide sort of utility, good answers while ensuring privacy, even if you're doing sort of differential privacy. So what we did was we came up, and I don't have time to get into this, but we came up with a unique way of representing the data. So we created this app that will let you put in your symptoms, and that will be stored in a secure database. So we are acting as a trusted curator here, but then there's an intermediate representation that is built over this data, which is then used to answer any number of questions over the data to ensure that no matter, even if you ask like 1,000 questions, the privacy risk to anyone does not keep on increasing. It's basically bounded over there. And this app has actually been developed. So there were a bunch of challenges, as I said, from the technical level. It's spatiotemporal data, it keeps changing. You have an arbitrary number of queries. And actually, if you want people to use it, it really needs to be able to work fast as well. The results have to be usable, and they have to work actually for the specific situation at hand, in this case, the COVID pandemic. And surprisingly, apart from the technical challenges, one of the biggest challenges was with the rapid development effort, getting it certified by the Play Store and the App Store so that we could have it out there. But we managed to do that, and actually the app is out there. And if you have an Android phone or iOS, Apple device, you absolutely can get it and put in your data through it with a guarantee of privacy. One thing that I wanted to point out, we have looked at this data, and yes, we've gone through the IRB and all of that. The good news is that you can actually get very, very close to the non-private results using these techniques as well. So these bars that you see are basically the original data and then the private data. The stacked bars sort of give you the idea that they are roughly the same. But just to give you a better view, on a particular date, for example, you can see the heat map for the private versus the original. And as you can see, basically the relative ranking, not just at the county level, but even within counties, it turns out to be exactly the same. So again, I don't have time to go into the details of this, but in terms of hotspot tracking or ranking, it's very easy to sort of get exactly similar results. And you don't lose out on accuracy by sort of doing this. So with that, I'll basically stop and basically say, yes, you should use the app, and the links are there if you want to use it on your Apple device or your Android device. And I'll stop right there. Thanks.
Thank you so much, Jaideep. And feel free to put your links in the chat for other people to check out. So
sure.
Thank you so much.
Thanks.
Great. Well, if Colby, if you're on, would you mind letting us know? If not, we can move on to another researcher.
I don't see him yet. I'm emailing with
Okay.
him, so I think we'll move on.
Okay. All right, great. Then I'd like to introduce Olga Wilhelmi from the University Corporation for Atmospheric Research. Olga, are you ready?
Yes, thank you so much. Can you see my screen okay?
Sure, yes. If you want to just go into presentation mode, so your slides are on full screen.
Perfect.
That looks great, thank you.
All right, well, thank you so much. So first of all, I would like to acknowledge my team, the project co-PIs, Mary Hayden and Peter Howe, and also our collaborator, Cassie Olenek. I work at the National Center for Atmospheric Research, which is managed by University Corporation for Atmospheric Research. And I also wanted to acknowledge National Science Foundation for funding this work. So this project is about responding to extreme heat in the time of COVID-19. We have many years of research that have shown that extreme heat is the leading cause of weather-related mortality worldwide. And there have been numerous studies that have assessed heat health risks, characterized population vulnerability, and also assessed the efficacy of different protective measures. In the beginning of the pandemic last spring, it became evident that many of the safety nets that have been put in place to cope with and respond to extreme heat may be disrupted. And many people could be placed at risk from extreme heat during summer months. So the goal of our work was to better understand and quantify how the COVID-19 pandemic can affect the population, heat risks, perceptions, coping strategies, behaviors during the summer months. And in this work, we designed a nationally representative survey of 3,000 American adults. That was a georeferenced survey that we conducted in 3 waves. The survey had questions about, excuse me, questions about the COVID-19 and extreme heat risk perceptions, experiences, self-reported symptoms of heat stress, household coping capacity, self-advocacy, and protective behaviors. And our sample was recruited via Ipsos Knowledge Panel, and for data analysis, we used mixed effect regression models. So on this slide, I have only a few highlights from the survey. So we found that 82% of the US population were worried about the health effects of COVID-19. In comparison, fewer people, but still more than half of the US population, 58% of the American adults, were worried about the impacts of extreme heat. We also saw that the millions of people reported negative heat effects. 19% experienced heat symptoms, 12% reported reduced work productivity, and 15% reported feeling too hot in their homes. And despite the widespread use of air conditioning, we found that 13% of Americans reported that the high cost of electricity prevented them from cooling their homes effectively. We also found that some of the COVID-19 pandemic conditions decreased the coping capacity of the US population. We saw that millions of Americans lost their jobs or income, or found it more difficult compared to a normal summer to seek medical care, leave home and go to an air-conditioned place, or to check on friends and neighbors. So in the series of mixed effect models, we looked at, first of all, the effect of geographic and socioeconomic predictors of negative heat effects. And here I have an example of heat symptoms. And some of those predictors also included the access to air conditioning, including having air conditioning or having air conditioning but not being able to use it because of the multiple barriers. So for example, we saw that people with incomes of less than $30,000 per year were 26% more likely than average responded to report heat symptoms. And also people who reported barriers to using air conditioning, even though they have air conditioning at home, were 125% more likely to report heat symptoms than people who had air conditioning and were able to use it. So then we also assessed the added effect of the pandemic. For example, people who said that it was more difficult for them this summer to change their daily routine to avoid extreme heat were 70% more likely to report heat symptoms than people who said it was less difficult or more different than this summer. So when we summarize a significant test for predictors for 3 negative heat health outcomes, which includes decreased productivity, feeling too hot at home, and having heat symptoms, it is evident that access to cooling played a really key role across all the different outcomes. We also saw that the pandemic-related factors, including social isolation because of the pandemic shutdowns or other restrictions, were significant predictors. And as you see on this graph, the number of those factors increased with the increase in severity of outcomes. And among all the socioeconomic groups, those who were more likely to report negative heat effects last summer were women, low-income population with income less than 30,000, Hispanic, mixed race Americans. And geographically, we saw that in the South, in the West regions of United States, we had more people that were affected by negative effects of the heat. So one of the key findings from this study is that the COVID-19 pandemic indeed did exacerbate existing systemic vulnerabilities to heat and also widen the range of vulnerable population. So in our next steps, we will be focusing a little bit more deeper on the analysis of spatial and temporal variations in people's experiences, risk perceptions, behaviors, and self-efficacy, as well as we will be taking a look at some of the broader environmental and societal factors that may affect risk perception and decision-making. And we also hope that this work can contribute to a better understanding of the multi-hazard risks and intersecting vulnerabilities as we are looking at this work in a larger framing of risk and vulnerability, especially with a multi-hazard situation. So I will stop here and I will be able to take any questions either offline or in the chat. Thank you.
Thank you so much, Olga. All right, so then let's, so Colby, are you ready to present? Have you connected to audio?
Yeah.
Oh, perfect, great. So in that case, I'll help.
Now I have backup, yeah.
That's great. Okay, so I'll help you share your slides then. Great.
So you're gonna share my slide, right, Helen?
I can help you share it.
Yeah,
if that would be
yeah. I'm afraid my PC will shut down my computer again. Yeah.
All right. Okay, feel free to start whenever you're ready.
Yeah. So my name is Colby An. I'm a CEO of Akeracor, and I'm going to present our research area, the project that we have funded by NSF. SBIR. Next, please. Yeah, and my company started in 2016 when I was a faculty at UC Santa Barbara, based on the surface treatment technology inspired by marine bioorganisms. And when pandemic started next, we thought we can help to address the pandemic by applying our surface treatment technology for many surfaces, because we can make antimicrobial surface to kill the viruses and bacteria on contact continuously. And we know that CDC wasn't very helpful because they are also some sort of in confusion that they said we don't need mask in the beginning, but it's common sense that covering your face when you're coughing or when you're sick is absolutely common sense. But there were confusion, and they also said we have to wash our hand more, and they gave us a direction that we need to hand at least 20 seconds. But they did not give us how to sanitize your hand with sanitizer, because alcohol sanitizer are 80% in the US and in the world used in this pandemic, but it's only effective when you keep your hands wet in alcohol for 15 seconds. But most of the people use alcohol hand sanitizer, they apply it after 2 seconds, they try to dry it up because they don't want this, right? Then your hand is not sanitized. So, and contact transmission was one of the major route of this pandemic and infection, because you touch the surface after you touching your face or eyes, and but I think so So we instead try to, explain to government officials or CDC. Rather, we decide to provide better product that people can use on their hand or as a disinfectant on surface, that the coating can kill virus and bacteria continuously, so that they don't need to worry about those instructions. So, and also before pandemic or after pandemic, there were like more than hundreds and thousands of people die by secondary infection from hospital or from infected from friends and family. It was there. It wasn't. It's not new. It was there already. And we need to address these issues, continuously. So next. So, but current approach is for treat those patients, especially in ICU, was using biocide releasing coating that's potentially genotoxic and cytotoxic, and also it takes longer time to kill germs. And other approach that people taking is cationic polymer coating that people uses right now, and all the 24-hour protection disinfectant and sanitizers in the market uses this single charge cationic polymer coating, but I will show you the result later. It's not very effective. So our approach here was to provide much more effective and inexpensive surface coating that is two charges. Gemini charges ammonium compound that is like orders of magnitude stronger, higher surface activities than the state of the art. Next, please. So this is kind of cartoon image of how this surface coating nano, like it's gonna be like 2 to 5 nanometer thick coating, can break the membranes of cell membranes of virus and envelopes of virus and cell membranes of viruses. Next. So we did some proof of concept studies that it shows that our coating can continue to kill the viruses and bacteria on the surface, and it makes the surface very hydrophilic. And next. So this is also other tests that we based on the ASTM method, time kill determination. You see that in 15 seconds, this Gemini coating can kill it completely in 15 seconds, but 70% alcohol still leaves some bacteria on the surface. Next. And 24-hour test, alcohol, once it evaporates, this is like porous textile product. So it could still, some residue of alcohol remains on the surface for 5 minutes, so it's still effective. But once it evaporates completely, it then can't kill anything on the surface. But whereas our Gemini coating can kill for 24 hours. Next. And it's even porous surface, you see that it multiplies. Next. And this is non-porous surface such as glass and plastic and metals that use for door handles and surface countertop, and alcohol evaporates in 5 to 10 seconds, and it loses its effectiveness. And next. And the comparison between ours and state of the art, which is single charged ammonium coating that uses in airport and airplane. These days we use this coating so you are safe for 24 hours. But the problem is, yeah, there was coating that can kill the germs and bacteria and viruses for 24 hours. But how long does it take to kill it? In 5-minute test, it can't kill anything. Coronavirus, it only kills 70% of coronavirus for 5 minutes. So yeah, if you wait for an hour, it will kill the virus. But in those hours, how many people will touch the surface? Like hundreds and thousands. Then you get all contact transmission occurs. So compared to our new Gemini ammonium coated surface, it kills everything in 100% in 5 seconds. We need this kind of technology, unless CDC provides much better instructions and direction that how people will stop this transmission, contact transmission. So next. So currently we are working with some large distributor to distribute this technology and license out to some companies, but we're still looking for other strategic partners, also university, that we can do more, dive deep into, test more viruses and bacteria to see if there's any other area that we can help with this coding technology. And next, please, Helen. So the markets are huge, and it's antimicrobial catheter alone is $40 billion market, and disinfectant is like 10 billion, 25 billion, but it only goes up. So there are lots of huge market opportunity here. And next. But more importantly, we can save lives with this. And it's not just about SARS-CoV-2. So it's more about upcoming dangerous, contagious diseases, infectious diseases. We can prevent those pandemics with this. Next. This is our members of our team, and there are actually two people from Columbia University and working with us. So thank you, and I'll take any questions later.
Great, thank you so much, Colby, and thank you to all of the researchers who have shared with us their insights today. So let me move on and share my screen one more time. And thank you to everyone who's been entering questions in the chat. Before we go over any unanswered questions, I just want to talk a bit about how you can learn more about different COVID research that's happening now, and also how you can stay connected with the COVID Information Commons. So first of all, the recording for this webinar will be available on the covidinfocommons.net website. You can check out the individual lightning talks under the Meet the Researchers tab. On our events page, you can also stay in the loop about upcoming events. We'll be holding our next KIC research webinar in May, and then we'll also be holding one in June. And you can sign up for a mailing list at this link if you would like to stay updated about these events, also different opportunities. And you can also join the KIC community on Slack to engage with other researchers and potentially identify collaboration opportunities. And finally, please email us if you have any questions about the COVID Information Commons, or if you're interested in presenting your NSF or NIH-funded COVID-related research at a future KIC webinar. So I can leave the slide up maybe, and then in the meantime, we have several great student assistants from the Northeast Big Data Innovation Hub with us today, helping to manage the chat, take notes. So maybe now, if Abhishek, you want to go over any questions in the chat that maybe haven't been answered.
Hi, Helen. Thank you so much for asking me. But fortunately, I think all our speakers have been really active in the chat, and they have answered all the questions that were asked. So we don't have any questions that are unanswered at this point. So
thank you, Abhishek.
Thank you so much for everyone for answering the questions.
And I'll hand it over to Florence for any last words.
Oh, thank you, Helen. Well, this has been wonderful. And as we look at the future KIC webinars, as we mentioned, we're really delighted to invite our NIH-funded COVID researchers to join us as well to present. We're also looking at a couple of things. And one is that I've also worked on transition to practice programs with the National Science Foundation before. How do we transition research to practice? And a number of you have great examples. UW-Madison, Colby, what you were just talking about, Lalitha, you plan on deploying. And so one of the things that we're thinking about is adding like a transition to practice, piece on the COVID Info Commons, how people can look at the stuff that's ready for prime time, so to speak. And it takes time to get there. But if any of you are interested in being part of that, when you're ready to do that, let us know. You can always email us at info@covidinfocommons.net. Go to the KIC website and you can find us. And it would be, wonderful to be able to have that information out there, because that's why we do the research, so that we can help address societal challenges like COVID. And as Helen mentioned, we'll be having follow-on KIC webinars. Please invite your friends. And if there are any other questions we didn't get to or you didn't have a chance to type them into the chat, we'd be happy to listen to those questions now or answers.
Florence, I did want to bring up something. I know the NSF has these convergence accelerators. I mean, I'm certainly aware of it in particular critical infrastructure areas, but so could this be, I mean, you know, sometimes you need additional funding to bring it to that fruition state, which has been a bit of a challenge. So
yeah, so if you have an opportunity or a challenge like that, feel free to bring it to me. And we're actually funded by the Convergence Accelerator, the COVID Information Commons. And I've done transition to practice work before on cybersecurity with the NSF Cybersecurity Center of Excellence. And one of the goals of the Convergence Accelerator is to, of course, help with convergent research, multidisciplinary research, but it's to accelerate it into practice too. And so they're very focused on that. As a matter of fact, one of the leaders of it, Doug Mon, used to lead cybersecurity and transition to practice at the Department of Homeland Security. You may know Doug. So he brings that with him in his heart. And I know a lot of the program officers are interested in that, as I am, and as the government is and our citizens. So I'd be happy to chat about that, Lalitha, and let's see, you know, what you think you need. I also think there's additional funding maybe going to NSF from the government with the latest act that was just signed. So there may be some opportunities there for some people if you reach out to your program officer. But I do want to talk about how we get this transition to practice. And, you know, when I look at yours, Lalitha, I think ASU and then, ooh, how do we get it to other schools, you know, right? That's what I start thinking about is the scaling then as well. But first, you know, getting it out there and vetted, and you have a maintenance plan and a customer support plan and all that fun stuff, right, that you have to make sure you have. And I'd be happy to chat with you about that.
Hello.
Great. Yes.
My name is Samuel Edunya. I'm at Meher Medical College in Nashville, Tennessee. So we have a couple of NIH supplements on COVID, and one of them in particular is actually trying to examine factors which may contribute to the vaccine hesitancy and how to address those in underserved populations. And I'm wondering, would any of these various models that talk about today be sort of modified to or be adapted to such scenarios in terms of looking at hesitancy of vaccine uptake?
So if any of the researchers would like to respond to that, I think, Dan, you were talking about a little bit, and some of the other researchers.
Yeah, happy to. Samuel, do you mind, I mean, we have the model. Do you mind reiterating the question just so I understand how it might be applied to your current context and the questions you're asking?
Right. So will your model be applicable for looking at factors that contribute to the vaccine hesitancy in, say, one county or the other and so forth, and how best to address those?
I think it very well could be. So what I didn't talk about today was we do have some, you know, we've done some analysis on the survey itself and who is hesitant versus not. And we, you know, and I think there was actually a comment in the chat that I think is important, right? Depending on which part of the country you're in, the imbalances cut across different demographic lines, right? So in an urban area like where I am, the bigger issue is the distinction between predominantly white and Asian respondents versus more historically disenfranchised Black Latinx populations being more hesitant, right? But as someone pointed out in the chat, you know, I think the point was in rural Tennessee, right? The issue is more rural white males, right, who are more hesitant, and we're seeing a lot of that in the reporting that there's different distinctions across the country. So I think that in terms of survey analysis, but also leveraging the survey and then putting it inside of a model the way we did, it's going to depend on, you know, your local context and the local kind of narrative and discussions that are being had as applicable. I mean, there certainly could be some real important parallels, you know, and maybe, you know, socioeconomic or gender differences or so on and so forth that we could reveal if we have parallel surveys. But I think that the insights of our model would transfer to a rural context if one acknowledged that what we classified by race might have to be classified slightly differently.
No,
But
our
then,
project is actually based in Nashville, Tennessee. Nashville is the largest city in Tennessee, and so
yes.
and it's I won't say 100% multiracial, but I would say that you have a reasonable number of African Americans and Latinos in this area. So you have multifactorial issues, whether it's socioeconomic issues, racial issues, and some people believe they are in the South and they don't take vaccine, or they won't do whatever it takes to to make it happen. So that is one of the things we are interested in looking at, and it would be nice if your model could be adapted to look at those.
Absolutely. I mean, why don't you contact me offline and we can continue the conversation and see how it can be applied.
All right, thank you.
Yeah, Dan, why don't you put, oh, I'm not muted, good. Dan, why don't you just put your email into the chat if you wouldn't mind,
Yeah.
so Samuel has easy access to it.
Yeah, I'll just send that straight.
Right.
And then, Samuel, I'm really glad you brought this up, not because I'm happy about the issue, but we're all dealing with it. And I have friends that feel that way, in different ways, vaccine hesitancy. We want them to be safe and we don't want them to die from COVID. So I'm wondering, you're talking about your NIH supplements. We have NSF funded researchers here.
Mhm.
One of the things we're thinking about in these KIC webinars is to actually have some topically focused ones. Since vaccine hesitancy is probably going to be around for a while,
Right.
right? It's not going to be over next month. It'll
That's right.
probably go through at least the end of this year, if not
Mhm.
beyond. That maybe we could do a call to the NIH and NSF funded COVID PIs
Mhm.
and ask if they have an interest in a topical webinar on vaccine hesitancy.
Yeah, it'd be a good idea, definitely.
And then you could be one of the presenters to present, the perspective that you have and the challenges you're addressing and your research, and then we can ask for others.
I think it'd be nice. See, one of our supplements also focuses on specifically African Americans and Latinx, and it's trying to recruit women who are associated with YWCAs in Nashville and Memphis and El Paso area, and then identify barriers for vaccine testing hesitancy and how to address those. So that would be an interesting project to talk about. And then we have one that is focusing on new African-American mothers and their newborn babies. And there is the concept that perhaps newborn babies can develop immunity from breastfeeding. And there are a number of literature publication to that effect. And so one of the projects specifically looking at how to adhere to the COVID-19 breastfeeding guidelines and so forth, and trying to assist African mothers to address this issue. So any of those could be very good things to talk about in the future.
I agree. We actually had a researcher on a prior KIC webinar talk about breastfeeding, and she actually presented her research on that. So I know that's another topic as well. So these are going to be going on for a while, unfortunately. COVID-19 is COVID-21 right now. It'll probably be COVID-22. I don't know what we'll call it then, if we'll get it a new name or not, unless there's a confluence with another zoonotic, which I hope doesn't happen, but you never know. So yeah, I'll reach out and let's find these other NSF and NIH funded researchers who could talk about this. It's very timely, it's very important, and it's a social, it's a social science issue. It's not, just the hard medicine science. It's the sociology side of it. And there are some sociologists and social scientists that I'm working with in the natural hazard space and humans in general, and they might be interested in joining the discussion too. So thank you so much for voicing that. And Dan, thank you for presenting your research on that and the others who did. I think it's a very interesting topic. Thank you very much.
You're welcome.
Very good. Any other comments or questions? This collaboration is always great. We always learn from each other and come up with even better ideas. Okay, great. Then I think we're done for today. Helen, thank you so much for being our amazing master of ceremony. I'm very proud of you as an undergraduate at Columbia. It's wonderful to have the students leading us into the future, because you will be for a long time. So thank you for that. And thank you for all the researchers and participants today, the presenters, and those of you who've been actively communicating or listening and learning. It's all very important. And we hope you join us for the next webinars. You can send an email to info@covidinfocommons.net, go to the KIC website, sign up for our newsletter, and we'll make sure that you know about it. And we look forward to further discussions as we address the COVID-19 pandemic. Okay, thank you very much, everyone. Be safe. Have a nice day.